Alrighty. Well, good morning, Amy. Can you hear me?
Good morning.
Good morning. Um, so, let me start by saying that next time, we'll discuss projects. So if you look at the syllabus, you can see there are short descriptions of the various projects, and you got to pick by spring break. Okay. So we'll talk about them next time. Then I'll give you a few weeks to think about it, and then before spring break, you settle on which one you want. Okay. So last time there were a lot of discussions about characteristic functions. There were a lot of discussion about characteristic functions, and so what we're going to start by doing here today is to compute. It's going to be to look at examples of how to compute them. And we're going to use martingale techniques how to use martingale techniques to calculate an expectation of the form. So we need to settle on what variables we want to use for the Fourier variable. We've been using t. We can try to continue, but it typically ends up being a mess. So t, we should have a u here, and then say y capital T. We calculate this thing. U is a real number. And y is a diffusion. So a diffusion means that you look at its dynamics, and it can be written as a drift mu and martingale term right where mu and sigma you just functions. Right, so a diffusion, something that has this form, it has a drift term, there's a dt term, and there is a sigma dB term. So remember, this is just shorthand notation for the long way of writing it. So just recall. So recall the meaning. Star. It is that you integrate both sides. So you integrate, say, dyt from 0 to capital T. Right, so on the left-hand side, you will get yt minus y0. And on the right-hand side, you would get the initial point and then an integral of mu and sigma with respect to the bounding motion. So then you can move stuff around. You can move the yt to the y0 to the other side, and you get yt is y0. So it's wrong. Why there should be no y0 here? You're integrating dy, so I'm just plugging in what dy is up there. Too many mistakes here. So now you move the y0 to the other side, and you'll get this this integral form of y. Right, so this yt is a diffusion. Some people also call it for a stochastic differential equation. And SDE. But the meaning behind this, the meaning behind what we're seeing here is really this integral form. And so it's more appropriate to see it like a stochastic. This is a stochastic integral equation. But people still call them stochastic differential equation, even though the meaning is really an integral equation. Are we good so far? Any questions? Right, so for us, we're going to be interested in calculating the characteristic function when y is specified by a function mu and a function sigma. So the two main examples that we're going to be interested in. So today we will consider the Ornstein-Uhlenbeck process. The Ornstein-Uhlenbeck process, this is also just called OU. So the OU process, we need to specify the drift function. So the Ornstein-Uhlenbeck process has mu of a, this is an affine drift, so it's a kappa, and there's a theta minus an a, right? This is for a and r. So here we're going to let kappa, theta. We also need something for the sigma. So you have sigma of a. This is just a coefficient beta. So you let kappa, theta, and beta. You're just constants. So this is an affine function. This is a constant function. So this is affine. And this is just a constant. That's the Ornstein-Uhlenbeck process. It has a constant drift, and it has a linear drift in A, and it has a constant mobility. So if you were to write out the dynamics, this form here, if I were to write out the dynamics, I would have dyt would be, and then I plug in instead of A here, I'll have y of t. So I'll have kappa theta minus yt dt plus beta dbt. Right, so it's a stochastic differential equation because there's a y on the left-hand side and there's a y on the right-hand side. The other one we're going to be looking at is the square root process. Square root process. The square root process, this is also sometimes called a CIR and filler. So again, we're going to have these coefficients. We're going to be considering constants, kappa, theta, and beta. The constants, and we're going to take mu to be exactly like in the Orson-Uhlenbeck case. Mu of A, this is kappa theta minus A, and the sigma, this is the new thing, it's going to be beta, but now there's going to be a square root of A, and that's why it's called a square root process. This here is, now this is affine, and this one here is a square root. Okay, so then if we were to look at the dynamics, we will go back up to dy, this form up here, and I'll plug in these two functions. So I'll replace A by yt on the right hand side, and we'll see what we get. So we'll have dyt. This is equal to mu was kappa theta minus A. So this is kappa theta minus yt. Plus, and then the volatility, this was beta root yt dbt. So now we see on the right hand side, we have y's two places. We have it here, and we have it here. So one thing to note here is a major difference between OU and square root processes is what? So OU, this is going to be normal Gaussian. So yt takes values in R, and the square root process this is going to be well, you'll see this in the homework, this is going to be chi squared. And one thing that implies is that yt is positive. And you can see it coming here. If you look at this one here. If you look at this one here, if yt is equal to 0, if yt is equal to 0, well then the change in yt, is going to be kappa theta minus yt. Well, that was 0, so that's going to be kappa theta dt. But because the other term right, if y is 0, this term here drops off, and this term here drops off, so you have kappa theta. So that means that the change in y is going to be kappa theta, which is positive if kappa times theta is positive. What it means is that you have your process, you started out here, if it moves around And if it at some point it hits 0 there, this is path of yt. We have a path of yt, it starts out at y0, and it moves around. And if it at some point gets down to 0, then what will happen is that this kappa theta is going to move it back up, right? Because the change in y then is going to be positive, so it's at 0. The change is going to be positive, and it's going to come back up. You will not have something like that for the Ornstein-Uhlenbeck case. And if you look at it there, right, if you look at this for the Ornstein-Uhlenbeck process, this doesn't work. This is not true for the OU process. Say that yt is 0. Say that yt is 0, then what is the change in y? Will it again be kappa theta dt? But you'll also have beta dbt. Right, so this thing here could be positive, but this thing here, this is going to be Gaussian. Actually, you have something that is positive plus something that is Gaussian. This here can be anything. This is just something in R. Right, so there's a main difference between the two processes. One of them you can get to have, if we can make it positive. And the other one, condition that comes up, condition that for the square root process, there is a condition, and it's called Feller's condition. There's Feller's condition, and it says that yt is strictly positive for all t if and only if. So this is strictly positive if and only if, and then you look at the coefficients. I look at the coefficients, and I need to look up my notes. I don't make a mistake here. So there's Feller's condition, and it says that the Feller process, the one that has the square root part in the volatility, this object, the solution to this SDE here is strictly positive if and only if the drift is big. So that's my kappa theta. That was the one we had before. If and only if kappa theta is big. And what does it mean to be big? It means that it is bigger than 1/2 times beta squared. That's Feller's condition. So this is the theorem. And for the square root process, y is strictly positive if and only if the drift kappa times theta, those drift coefficients, the sufficiently big compared to the volatility, and the volatility coefficient is this beta. So today we're also going to be talking about we'll also talk about simulating paths. Just how to simulate these paths of these SDEs. and it's complicated to, for example, keep them positive, to keep the simulated paths positive. To keep the simulated paths positive, even though the actual paths are positive. So, so it presents a problem. We have this fellow process, and if I want to simulate it, it can become it can be really tricky to get the simulated paths to be of the same type, namely positive. So we're going to be talking about tricks how to overcome that. So in general, it's much easier. It is much easier. It's much easier to simulate real valued paths. Okay, so we're going to be talking quite a bit about this in the second half of today's lecture. We have more students now. Are there any questions or comments on what we started out talking about? So the first half of today's lecture, what we're planning on doing is using martingale techniques to devise a way to calculate these characteristic functions. And then the second half of today's lecture, my plan was to start doing simulation, how to simulate pairs of a diffusion like this one here. Are there any questions or comments? Okay, then I should also say for those of you that might not have been here in the beginning, so next time we're going to be discussing projects, and so have a look at the syllabus. There is a description of I forget how many projects, several, and the next time we'll talk about them, and then you gotta decide before spring break. So after spring break, you start thinking about it. Okay. So to move on, we're going to be doing these characteristic functions. Okay, so we will now consider. So the first example we're going to do is the Ornstein-Uhlenbeck process. So this is the OU. So you have your dy. So kappa theta, again, the constants, and the volatility is beta. And we're interested in the expectation. We're looking at the expectation of EI, and then it was U YT. Right? We want to know what is this equal to. And I think one of you, I forget who it was, it might have been Alice, it might have been Amy, who was asking, I think in the office hours, about we should just integrate out in the density. And I agree, if we would know what YT's density was here, we could do such a thing. Meow Yin has a problem with the internet. I'm sorry, Meow. We're having a lot of snow in New Jersey these days, and it's snowing like crazy here too. So we'll see how well the internet is working on my end. I also have all my kids home because of the snow, and so there are lots of computers in the house on the internet. I don't know how it's going to work, but we'll see how far we get. Worst case, I will record the videos and put them up there. So it was brought up, I think, in the office hours that like if I have the density, I can just integrate out here. Well, so the starting point is different. When we do these models like this one, we will start out with an SDE, right? So our starting point is the SDE. You're just given a formula for how the dynamics of Y look like. And now based upon those dynamics, can you tell me what this thing here is? And in general, the answer is I have no idea on how to do it. In some special cases, you can do it. And this here is a special case where you can do that. So let me show you how one can go about doing that. So the first step is you make it more general. You make it more general. You generalize. So instead of computing an expectation, you compute a conditional expectation. So you generalize the problem to calculating a conditional expectation. So here, this is where it becomes crucial that you keep track of all the coefficients. So U is the Fourier variable, right? U here is in R. This is the dummy variable that goes into the Fourier function. So that's the U here. And now you condition, and you condition on ft. So I want to know what this is. And now I want to know it for U and R and for t between 0 and capital T. So you take one problem and you make it more complicated. So that seems like a bad idea, but the thing that makes it all work is that this object here has a very special structure. And then we note, that this stochastic process, let me write it out. You know that for any U, this stochastic process here, indexed by T, this is a martingale. And how would one go about proving that? Right, so you pick a Fourier variable U. For any such U, this object here is a martingale. This is the thing that's going to make it all work. And it falls into a famous class of martingales. It's what's called a Levy martingale. For those of you that took 621 with me, you will recognize the word Levy martingale, and it's exactly the same as what we had there. The only little difference is that this here is a complex value because there's an I in here. So I should say here, this is a complex valued martingale. That's the only difference compared to what we had in 621. And so for those of you that were not in there, let me just recall why this is the case, right? So if you want to prove something is a martingale, there are a couple of things that we need to deal with. So the first one we have, so to prove this claim that it's a martingale, it has a special name, Levy. Paul Levy was a probabilist from France. He did lots and lots of stochastic analysis and stochastic calculus contributions to the field, and these kinds of martingales have been named after him. Let me give the short argument. So the first thing we have to do is to make sure that the thing is well defined, right? So first we have to check for integrability. So first we check for integrability. So what we want to make sure is that if I take the expectation of the absolute value of this thing, I'm going to get something that's finite. Right, that's my random variable. I want to make sure that the random variable is integrable, right? So I have a random variable. I want to make sure that it's integrable. Okay, so what does that mean? It has to be measurable. That's okay because it's a conditional expectation and they're measurable. And the second thing is that it has to integrate to something finite when I take absolute value. Right? So it has to be L1. Forget, some of you asked me about that last time too, right? So L1 means that you can integrate the first power, right? So I'm not putting any powers up here. This is just the first power, and that's the same thing in that L1 then. So it's integrable. And how would I prove that? Well, I have absolute value outside a conditional expectation. If I put the absolute value inside, I'll get something that is bigger. So then I'll have the expectation, and then I'll put the absolute value inside the conditional expectation. And so I'll get that. And by moving the absolute value inside, I'm going to get something that is bigger. And then we'll use the idiot rule. This is the idiot rule. The absolute value of this exponential here, we know what that absolute value is. This is exactly equal to 1. So then I'll have the expectation of the conditional expectation of a 1 given if t, right? But the conditional expectation of a 1 is a 1, the expectation of a 1 is a 1. So this here is equal to 1, and this is finite. So that was the first step. Martingales, this is a collection of random variables. And the first thing you have to satisfy is that they're integrable. Okay. Then the second step is that you have to satisfy that when I condition, I get the right property. Okay, so let's go back here. So we have a t that's running between 0 and capital T. So let me pick 2 time points in there. My pen is not working very well today. See if this is better. So let's take 2 time points in here. Let's take 0 is less than, and let's call the small one for s. And let's call the bigger one for t. And then the end is capital T, right? So I take 2 time points. And then for the object to be a martingale, so this just recall, right? That the expectation is like mt, I take a later time point, condition on an earlier time point. Right, this is what I want to prove. I take the stochastic process, look at it at a later time point, condition on an earlier time point, and then when I compute this conditional expectation, I should just get the value of the stochastic process at the earlier time point. Okay, so here I have my stochastic process. This is my MT. This is my MT. So when I'm looking at the left-hand side, I have the conditional expectation of ERUYT given FT, and then condition on FS. And then what? So now I have 2 conditional expectations next to each other. I have F capital T, that's at the later time. I have F little t, that's at the later time. Fs, this is earlier than Ft, this is earlier than t. So Fs here is inside Ft. So if we have Fs is a subsigma algebra for Ft. And so we can use, does anybody remember what the word is that I'm looking for here? What is it we're going to use? Anybody remember? Alice says iterated expectations, very nice. So we can use iterated. Thank you, Alice. So we can use iterated expectations. The smaller guy wins. The smaller guy wins, and we are done with the double conditional expectation. We just get EIUYT given, and then the smaller one, right? And that was what we set out to prove. This here is exactly my MS. Is exactly my MS. So this is really true. It is a martingale and has a specific structure. It's called a martingale. You take a random variable and you condition. When you do that, you're going to get a martingale. So as usual, this is the warning note. It doesn't always work. Right? This is just a warning. Like while, so you will know that this thing here is this is okay. That's the one we just had. But if I start playing monkey, if I start looking at E, I, U, and then maybe I'll start looking at YT minus Y little t, given FT. And this is not okay. It's okay. This is a martingale. This one here is not a martingale. And you can see it. If YT, we can pull it outside. Right? This becomes exactly e to the minus IU YT times the previous one. Right, this one here is a martingale. But then I have a product. And this may or may not be. This is a martingale, but the first part can ruin it. All right, so look out for the T's. Let's see if I have a red pen here. Look out for the T's. When you do the structure, there can only be one T here. Here you're going to have two T's, two little T's, right? There's a little T here, and there's a little T here. In general, that does not work. This idea, this way of proving that it's a martingale, it works when there's just a little T here. If you have two of them, it typically fails. Right, so one T, when you condition, this is okay. If you have a condition T, and then you also have something inside that depends upon T, then it doesn't work. So just look out for that whenever you use this. Okay, so that was step number one. We generalize, and we seek to compute something that is seemingly much more complicated. But this seemingly more complicated structure has actually a martingale component to it, and that's what's going to make it work. That was step one. So let's do step two. So step two. Maybe I should call them A and B. So this is A and B. So B is, you can use the martingale representation theorem. Have you guys gotten to that point yet with Professor Pham in 622? So martingale representation will say that martingales, they can always be written as stochastic integrals. So you will have the D and then this conditional expectation. This is going to be equal to something here, and then D BT. So martingales, they're given as stochastic integrals. Right? So remember this D form, this is nothing else than saying, maybe we should call this process for something. So The textbook likes to call this here for delta. To write this, so we can use martingale representation to write it for some delta t. So all martingales are given as stochastic integrals with respect to Brownian motion. So remember, this is nothing else than shorthand notation for, that was what we had on the first slide. So I just take the initial value. So that's when t is equal to 0. This is when you just get the expectation. And then the stochastic integral. So the martingale representation allows us to write it, this martingale here, as a stochastic integral and then plus a constant. And so we can now try to compute. So we can calculate what this delta here should be. And this is part of a much bigger picture. Of what's called the Clark cone formula. And I feel compelled to say this because Cone is well, he retired very recently from Rutgers. Some of you might have met him. He retired a few years ago. Daniel Cone. He was Clark did it in some cases first, and then Cone he generalized it. So calculating what this integrand here is, this is a big deal in math finance. When you do it in 622, this delta that you'll find there is going to be the replicating portfolio. What we're doing here is we're using it to calculate these characteristic functions. So this is a quite important part of stochastic analysis for quantitative finance. So let's get to it. But we know that it has this form. It's a martingale. Okay, so what are we going to do is, so to get started here, we're going to say, well, let us conjecture that this martingale here has a specific form, and the form I'm going to conjecture is going to be of the type E, and then here I want to have an A, and I'm looking at capital T minus little t plus another function B t minus t times yt. So this here amounts to, if you ever had a class, for example, if you saw ODEs in a calculus class, this is like a guess and check. This is like a guess and check approach. We're going to come up with a conjecture, I guess, and then we're going to see if it works. And of course, you can be lucky that it works, and you can be unlucky that it doesn't work. If it works, then you're done. If it doesn't work, well, then you're kind of back to square one. So here's one conjecture. Let's conjecture that this object here has that form for two functions. So A and B, they go from 0t to R. They probably go into C, huh? These are complex valued. complex value, right? So these are two functions evaluated at t minus t and capital T minus t. So this conjecture has this form, and let's try to figure out, let's start to calculate. So now we're going to describe. So next, we describe A and B by ODEs. Okay, how will we do that? Well, we will apply Ito's lemma. Okay, so we're going to use Ito's lemma. We're going to use Ito's lemma to calculate the dynamics. So you have d of that thing, e to the a t minus t plus b t minus t yt. What is it going to be equal to? Well, what we know is, because it's a martingale, we know that the only thing that can appear on the right-hand side, will be a Brownian motion term. There are 0 dt terms over here. So whenever we apply Ito's lemma, it has to be the case that there will be a 0 times dt plus whatever is left dbt. All right, so let's get to business. We're going to calculate derivatives. To use Ito's lemma, we need a function. Okay, we have a function of t, we have a function of yt. So let's look at the function. F of t and x. This is equal to, so that's what we want to do, right? We want to calculate these dynamics. So f is e to the a t minus t plus b t minus t times x. The first derivative, I'm going to drop t and x's here, it's just too much to write. The first derivative is going to be what? That's going to be derivative with respect to t. Okay, it's an exponential, so I'll get f back times something, and now I need the derivative of the inside with respect to little t. So I'm going to get a prime t minus t, and then there's a minus 1 coming in. So that's one term. I need the derivative with respect to t, little t of this guy. That's going to be the same, minus b t minus t x. There's going to be a dt after that, and there's a derivative. So that was f1 dt. Maybe I can just eliminate these dt's and put them back on when we do the formula. So this was the derivative with respect to the first entry, little t. And then we have f2, so that's going to be the derivative with respect to x. So it's the same story. You're going to get f down, and then times, now we did the derivative with respect to x, so we're going to multiply here on b t minus t. And then I also need f22. So I have to take the derivative with respect to x of this guy. It's going to be f times, and then I'll get b again, b t minus t squared. And so now we're ready for Ito's lemma. So Ito gives me that df t yt is equal to what? Well, first we need f1 t yt, and then I need dt. And then when I take the derivative with respect to the second one, f2 t yt, and then I need dyt. And then we need the new term because there's credit variation in y, so I need 1/2, and then the second derivative, f22 t yt, and I don't know how does Professor Pham, how does he like to write credit variation of y? There are many ways to do it. The way that I favor is to write this as a d, and then these pointy brackets of yt. Right, this one here, this is the quadratic variation this is the quadratic variation of y. I'm not sure other people write it like some people you might also have seen something like sometimes you'll see something like dyt, or you might have seen something like dyt squared. You might also have seen there are people that will write this as these brackets. There are many ways to write this quadratic variation. And so now what we do next is we plug all this stuff in. We will write this here out as, well, the first, you can see all the derivatives, they have the common factor of f. Right, so we start by putting f outside. Start by putting f outside a big set of parentheses, and then we plug in all the terms. So the first one is f1, this is the one that comes with a minus and a prime t minus t, dt minus b prime t minus t, and then there's an x is replaced by yt. So that was that guy. And then you have f2. f2 again has an f in it, it goes outside, and then I have a b. So then I get b t minus t, and then dyt. dyt, this is where we started out a long time ago. It was this one we had all the way up there, kappa theta minus y dt plus beta dbt. We take this object here, and that's where we use him. We're going to put him right in here. Kappa theta minus yt dt plus beta dbt. And we also need the quadratic variation term. That's the one that's new. We need a plus, a half, double derivative. So you're going to get your f back. It goes outside. I'm going to get b squared, bt minus t squared, and then the quadratic variation of y. We go back into the dynamics of the OU process. Quadratic variation, it only picks up stuff related to the Brownian motion. It doesn't pick up stuff related to dt, so I'll just have to focus on this one. And does anybody remember what the quadratic variation of a stochastic integral with respect to Brownian motion is? Yeah, it's dt, and here there's a coefficient beta. And what do you want to do with the beta coefficient, Alice? What do you want to do with the beta coefficient? Square it. Awesome. Very good. Very good. So you're going to get here, you're going to get here beta squared dt. Thank you, Alice. This is perfect. Right, so it's a mess, but it's not that bad. And what you do see is that there is a mixture of dt terms and then the Brownian term. Well, we know it's a martingale. We know it's a martingale, so this thing here better be, and this is where we're using that it's a martingale. This is a martingale property. We know here that this has to be just a stochastic integral with respect to Brownian motion. So here you have to find f of t yt, and then all the dt terms, they must vanish. So we're going to be left here with a beta dbt. This is so that's our delta. that was our delta from the mathematical representation theorem. Like that was our delta. This one here, this was our delta t. But of course, we need to figure out what f is. We have f is given in terms of a and b. And what are the functions a and b? To describe these functions a and b, so the no drift, IIE, is 0 dt term. The no drift requirement, it gives us, what does it give us? We're gonna have minus a prime t minus t. That's one of them. So let me scratch them out as we go along. So that was the first one. There's also a minus a b prime. And then there's a y. Then there's a dt term here. And you have kappa theta minus yt. That was this guy. And then there is the last one, the credit variation term. This thing has to add up to 0. So it's a long expression. But what we do see is that everything here on the right-hand side, this is affine in yt. This object here, this is affine in yt, right? So it's equal to a constant plus a linear function of yt. Right, so what you do now is, so an affine function is characterized by the slope and the interception, and you put these two to 0, right? So you collect terms. The first one you collect, it will be the yt terms. We put a 0 there. So you'll have here beta prime, and here there's another one. There's a minus kappa b t minus t. There's a y. And then the remaining term, so these are the constant terms. Maybe I should just call them remaining. They're not constant in t, they're constant in yt. So the remaining terms. So we're going to get a prime. And so here you're going to get plus b t minus t kappa theta. That was that guy. And then the credit variation term, the 1/2 b squared. So you see it's very, very close. Like we have a b prime is given in terms of b, a prime is given in terms of b. So the only thing that we need for this to become an ODE is we need the boundary condition. We need the terminal conditions. Okay, so let's try to get the terminal conditions going. We need the terminal conditions. If I look at my function here, f, t, and x, if I evaluate this function at if I evaluate this function here at f at capital T and x, f at capital T and x, I'm going to get e to the a evaluated at 0 plus the b evaluated at 0 times x. So that's my that's the function that I get out. This is the value I get out when I evaluate the function, a little t being capital T, a0, b0, and the x is going to come out. Okay, so what is it I want it to be equal to? So to get the boundary condition, this is given by a demand that f at the end, and remember we're evaluating f here at we're evaluating f at yt, so little t is replaced by capital T. What is this going to be equal to? That's the boundary condition, and let's have a look. What would be my martingale? Where do we have got a formula for it? This one here. What is that equal to? Well, if I take little t equal to capital T, so this is just a note that when t is equal to capital T, then the conditional expectation of E, I, U, Y, capital T, given if capital T, that's just going to be E, I, U, Y, capital T, because this is already if capital T measurable. So you see at the end, I'm going to get this value here. Okay, so I'm going to get here E, I, U, Y, capital T. And at the same time, on the left-hand side, I will have this exponential, and then it was A of 0 plus B of 0 times Y capital T. So the boundary condition is given by this. Okay, so what should be my A of 0 and what should be my B of 0? What should be my A of 0? What should be my B of 0? Well, A of 0 should probably be B. There's nothing here. So A of 0 should be 0. And B of 0, so now this one is gone. B of 0 should be IU. Right, which is a complex number. So this gives me my ODEs. So overall we have the ODEs. We have two of them decoupled. I have B prime of S, right? We just replace T minus T by S. So I'll move it to the other side. I'll get that this is minus kappa B of S, and I start out when S is equal to 0. When S is equal to 0, I have the value IU. I'm going to have my A prime equal to, move to the other side. This is equal to B of S kappa theta plus 1/2 B of S squared times the beta, and the A function starts out as 0. Are there any questions on this step? So I have my ODEs, and sometimes you can solve them. What kind of a function b here am I looking at? What function satisfies that b prime is equal to minus kappa b? What is my function b here really equal to? We write a formula here for b of s. Yeah, Alice is saying let's do an exponential. E to the minus kappa, e to the minus kappa, e to the minus kappa s. That looks good. And then there has to be correction for the initial point. This is probably going to go out in front. I should we just test it out? When s is equal to 0, exponential with 0 is a 1. That works. The derivative with respect to s, this is going to give me minus a kappa down and then times b. So that one works. And then a, how are we going to get a? Well, this is a feature that you'll see a lot. It has this, it decouples because the first one doesn't involve the second one. So this is like a triangular structure. The first one is by itself. It's like that Koleski factorization we had a few weeks ago. Like the first one is by itself, and then the second one is in terms of itself and the previous one. And so to get a, you write it at a is equal to, well, the initial point, and then you integrate a prime of say b dv. Right, and a prime was 0, so we are just going to be stuck here with an integral from 0 to s, and then you plug in a prime. This is b of v kappa theta plus 1/2 b of v squared beta squared. And now you can insert b and calculate. And so all in all, what you have now is, all in all, you have that this conditional expectation, like the u here, that value you have up here, this is the Fourier variable. You know that this is equal to e to the a t minus t b t minus t y t. And the one you want, so you just use this with t equal to 0, then you're going to get the characteristic function. This is equal to exponential a of t plus b of t by 0. So you can take the functions a and b that we found up here, plug them in, and now you have the characteristic function for the Ornstein-Uhlenbeck process. And we did not use anywhere. We didn't use anywhere what the distribution of y was. We just used the dynamics that we had to begin with. The only thing we used in here was that form. Are there any questions, comments on this step here? So this, some of you have seen me do calculations like this before. Some of you have not seen me do calculations like this at all. If you haven't seen any of this before, this can be a little bit overwhelming. Most students, they get the hang of it at some point, and I'm sure you will too. What I propose is we do one more example. Right, I had 2 examples prepared. I'll do one more example, and then we take a break and move on. So let's do one more example, which is quite similar to this one, but not quite the same. We're going to get a similar system to what we have here, but there'll be some changes. So let's do one more example. So the other example I had in mind for today was the fellow process, the square root process. So the other example would be it's almost the same as before. The difference is that there's the square root over here in the volatility. Okay, so now our goal is again to calculate the expectation E of y. To calculate the expectation, we consider, and this is going to be the martingale. We consider the martingale for t running between 0 and capital T. And now we go through the entire same exercise one more time. So let's try again. The conjecture. So let us conjecture let us again conjecture that the martingale can be written as this function of t and then yt, where f has this exponential affine form. So we need to find, so we need new ODEs. We need to find the ODEs for A and B. Just as before, of course, we're going to get different functions A and B now, but other than that, the structure is quite similar. So we need to find the ODEs for A and B, and the way we do it is very similar to before. We note that this is a martingale, so we compute the dynamics of the conjectured form, and so on. Right. As before, here we note here that if I evaluate f at the end, this is going to be e to the I u y capital T wait, and at the same time, this is going to be equal to e to the a of 0 plus b of 0 times y capital T. I want this to be true. Well, if I want that to be true, I need a of 0 to be 0, and I need b of 0 to be I u. So I get the boundary conditions exactly as before. What's going to be different will be the ODEs. The ODEs are going to be different. Okay, how do we do it? Well, we need Ito's lemma. So we need all these derivatives one more time. So we apply Ito's lemma. So I apply Ito's lemma, I get df of t by t. That would be just as before. This would be f1 dt plus what would be? It'll be f2 dyt plus 1/2 f22 credit gradation of y. So that's very similar. Now what's going to be different, of course, is going to be when we plug in what dy is and when we plug in what the credit gradation of y is, because that is what we're getting from the dynamics of y, and those are different. Like before, there will be no square root term. Now there is a square root term. So this is going to change how things work out when we plug in the various quantities into this formula coming from Ito's lemma. Right, so we start out here with f1. Okay, so we need to compute the derivative with respect to t. This is just as before. We'll have an f that's sitting outside. And then we have derivatives with respect to little t inside. So we have minus a prime t minus t minus b prime t minus t times the y. And then we have an f2 derivative. That's just going to give me my b. And so this is where the change comes, because here I have to put in my dy. And that's going to be different. So here I'll have something else. This will be my kappa theta minus yt dt plus beta, and then there'll be a square root now. And if you go back and look, this is quite similar to what we just did, except what we just had before, right? There was just a beta here, and now there's a square root. The drift is the same. These terms we had before, those are the same. And then we get the credit gradation, and that's going to change too. So that square root term here, this is a difference. The other difference is the 1/2 f22, and then the credit gradation, as Alice pointed out, the credit gradation of Brownian motion is dt, and then you have to square what's here. So it'll be the beta squared again, but now there's a yt. Right, so that is different too. When we looked at the previous one, there was the volatility term changed and the credit gradation term changed. This should not be f22, this should be my b. This should be my b squared here. And so we have a zero drift, zero dt terms. This is the martingale property. And so we collect all the dt terms, put them equal to 0. 0 is equal to minus a prime t minus t minus b prime t minus t yt plus bt minus t kappa theta minus yt. That was this guy, and then the last one, the variation term, beta squared yt. And this is again, this is affine in yt. So we can look at the yt terms. That will be the linear part. There's one here. So we have b prime t minus t is on the right hand side. And then we'll have minus kappa times b. That was exactly what we had before, but now there's a new term. There's another yt term here. There's plus 1/2 bt minus t squared beta squared. So that is new. And then the remaining terms, I have my a prime. What would that be? That would be my bt minus t kappa theta. So these are also a little bit different compared to what we were before. That term basically went from what it was down here to up there. And all in all, we get the ODEs. We get b prime of s is minus kappa b of s plus 1/2 b of s squared beta squared. Get a prime of s b of s kappa theta. And then we also need to add in the terminal conditions. Those we already worked out what were, so let me just copy and paste them. We did not change from last time. From last time, a started out at 0, so we'll put that in there. And b started out at IU. So here we have again this triangular structure, right? B is given in terms of itself. As soon as you know what B is, you can get A from integrating. Right? So B is by itself. A can be expressed as an integral of B. But the difficulty, of course, being that there's a square. You know, this equation, the top one, this is harder. Okay, so this is a triangular structure again. Start with B, and then you get A when you're done with it. But of course, getting B here, this can be tricky because there is a square here. Okay, so this is a little bit harder. And let me just, I'm not going to write down what the solution here is because this is something I want you guys to play with in the homework. But let me just show you some of the things to look out for. So if I go in to one of your homeworks, homework 3 here. If you look at what we have, if you look at what's in this last homework that I posted the other day, again, you see that there is a structure now that should be familiar. You have these functions, a and b. And here there's a square root process, like the one we're just considering. And you can see this function b, right? That's the one that was different. And you can see here comes out a solution that looks something like this. And it's not this exponential that I think Alice was pointing out in the Ornstein-Uhlenbeck case. This here is more tricky. There's an exponential up there, there's an exponential down there. And so the solution to these ODEs that we get when we're dealing with a Riccati equation, they're more complicated. And the question that we're going over here is exactly this one here. This is this exercise number 2. You take a Feller process and you find these ODEs that we just have. And now can you figure out how to solve these ODEs for C and D? And the key word there, when you start Googling around for it, is to search for something called a Riccati equation. So this is the key word that you want to use. Look up Riccati equations. That set you get out here for the equation for D. This is an example of a Riccati equation, and this is Riccati equations. These are the ones where the B prime is given as a square function of B itself, right? So there's a constant coefficient. There's no constant coefficient here, but then there's a linear term and there's a square term. These ones here are called Riccati equations. Spell it correctly. These are called Riccati equations. And they have closed form solutions. There's a closed form solution. Okay, are there questions about what we've been doing up to this point? Questions up to this point? If not, this is a good place to take a break. After the break, we'll do something very different. We'll talk about how to simulate these paths from SDEs, from these diffusion processes, and then we look at some code too, if I can get it to work. Okay, so let's take a little break, 10-15 minutes. Let's get back together around 10 o'clock, and then switch over to the other Zoom link. Okay, see you guys in a bit.